Howdy folks, a couple of questions in this homework ask us to go ahead and graph a direction field in CalcPlot3D and to go ahead and superimpose our solutions over that. It's a valuable skill. If you prefer another program, you're welcome to use it, but I want to show everyone how to do this in CalcPlot3D. So I'm going to go ahead and take a look at one of these questions here in our homework 2. And this one asked us to look at this initial value problem where here was the ODE and here were the initial conditions, or here was the initial condition. And part C says to graph the direction field for this differential equation and superimpose the solution onto it and to attach a printout of that. So I'm going to show you how to go ahead and do that. I'm going to assume that you've already worked this question by hand, or if you haven't, know that that's the first thing you're going to do, because before we can superimpose the solution onto it, we need to actually have computed that solution. So going to your favorite web browser, I'm going to go ahead and just Google CalcPlot3D. Folks, if you ever see a reference to a web link that doesn't seem to be working, it's because they've moved the location of this website. So just Google CalcPlot3D and you'll be okay. Whenever I pull this up, I usually just clear out this initial object that was in here, and I'm going to go ahead and tell it to plot a vector field. So our goal is to graph a direction field, which is sort of a subcategory of vector fields. And in this case, remember how these direction fields work. We're going to step one unit in the x direction. So this is our x coordinate function for the vector field. And then we're going to step whatever the appropriate rate of change is in the y direction. So here I'm going to enter in our differential equation. Looking back at the original, we see this was our differential equation. So this is our f of ty. I'm going to have to use x here because I'm in CalcPlot3D. I'm going to use xy. But this is the f of ty that our rate of change is equal to. So I'm going to go ahead and enter that into our direction field. So there's my x divided by y squared times the square root. And I believe we had 1 plus x squared. So again, I had to change the x's or the t's to x's in this problem. I don't think you'll have any problem following along with that. Let me just verify that I've copied that correctly. That looks good. So I'll tell it to plot that direction field. Oops, I'm missing a parentheses, so we better close that parentheses. And I tell it to plot that direction field there. A few problems. One, this is a direction field in 3 space, and we want to restrict ourselves to 2D. So I'll go ahead and do that first. Next thing I notice is it's not really hard, it's difficult to obtain a sense of the flow to these. So let's go ahead and add more vectors in here. I like to add about 20 vectors for a 2x2 grid, so we could do 20 and 20, something like that. Next thing you'll notice is that the magnitudes of these vectors are not 1, which is what we need them to be if we're sketching a direction field as opposed to a standard vector field. So I'm going to select the box that says use a fixed length for all vectors, so I'll do that there. And then I just take a look and I decide whether I like the way this looks. I might go ahead and sparse this out a little bit by dividing by a larger number. Maybe that's too high. Let's try that. That looks kind of like a nice direction field. One thing to mention is that there should not be arrowheads on here as we are graphing these direction fields. They shouldn't have the direction assigned to them, and instead it's when we draw any solution curves or superimpose those that we may draw direction arrows over that. Okay, so this is our direction field. So anytime you're asked to do this, this is how I would recommend doing this. For a first order direction field, we enter 1 for the coordinate function for x, and then we enter the f of xy, whatever we have when our first order differential equation is in normal form. That function on the right is what we enter here. That gives us our slope, our rate of change at any point for any collection xy. Okay, now I'm ready to go ahead and superimpose my solution curve to this. So let's go ahead and do so. I'm going to come up here and I want a function that looks like y equals f of x. I'm not going to be using z on here, but I always have the option of leaving it off. So this is the function y equals f of x. I select that. You'll notice I now have this new object that I can place on here. And what I'm going to do is I'm going to take my solution to the initial value problem that I found in part B here. Okay. So work through that and you've got that solution. I'm going to go ahead and enter it in here. And I believe that we found this solution to be, it's a cube root function. So I'll start, there will be my cube root. It's a little awkward to type a cube root in here, but you see whatever goes in here, that's what I'll be taking the cube root of. And I think we had inside that cube root, we had 3 square root of 1 plus x squared. Technically it was t squared, but again I'm using x's. And then minus 1 minus 3 square, oops, no slash on that, square root 3 square root of 2. And I don't know if I need this, I can't remember. I'm going to go ahead and put multiplication symbols in between the 3's and the square roots, just because I'm using so many programs right now. All right, and I think that's it. We go ahead and hit enter, and here you can see this solution curve placed on here. I want to do two things. One is you can see, I don't know how well you can see this, but these edges look a little bit jagged here. So I'm going to go ahead and put more grid lines in here. I'd like to do something like 100, but it depends on your computer and your internet strength, how well you're able to do that. 100 or maybe even 200. That makes that look a little bit more well-rounded, smoothed out now. The next thing I want to do is I'm going to click on this. That's a lie. We'll just leave it as is. So here is our superimposed solution curve. One thing that I found a little bit frustrating is it doesn't quite look like it's passing through the order pair -1, -1. In a moment here I'll convince you that it is. That has to do just something with the odd scaling in this CalcPlot3D. But sure enough, this is our solution curve. It's a curve that fits this direction field. And because this curve fits the direction field, it must satisfy then the original differential equation, and it passes through our initial condition of -1, 1. So that's all I wanted to show you on this, folks, and you're welcome to stop the video now. If you're curious, I'll just show you where I confirm that this actually does pass through the point. I'll just bring this solution over that I made. If I bring, it's not going to do it because of the, let me just bring over this solution that I made. And here you can see when I turn on these two graphs, you'll see that sure enough, yes, this does pass through the ordered pair -1, 1 as CalcPlot3D is interpreting these coordinates. So we did find the solution to the initial value problem. Thanks, folks. Let me know if you have any questions on this. Any other problem that asks you to use CalcPlot3D is probably going to have you sketch either a direction field or a solution curve like I did here. So hopefully that gives you an intro for working through those. All right, I'll see you in the next video or next time.